This is a brief introduction to atomic layer deposition at Tyndall National Institute, Ireland. I'd like to talk about the basic principles of the process, how it may be useful to you, and what facilities are available in Tyndall. To do this, I'd first like to introduce atomic layer deposition as related to chemical vapor deposition processes. I'd like to explain how it works, how you can appreciate the advantages and disadvantages of ALD. I would then like to make you aware of the current Tyndall infrastructure and how you may use it. In the basic chemical vapor deposition process, reactants are introduced into chambers as vapors. Key reactions can take place in both the gas phase and on the surface. The growth rate in chemical vapor deposition is determined by many parameters, including the flux of species at the substrate surface, the temperature of the reactor, and the pressure of the reactor. The key aspects of atomic layer deposition are similar to chemical vapor deposition, in that the reactants are introduced into the chamber as vapors. Unlike CVD, each reactant is supplied as pulses, separated by an inert gas purge or a pump-out phase. Each reactant pulse chemically reacts with the substrate surface, resulting in a self-limiting monolayer or surface modification. Subsequent reactant pulses can add further monolayers or chemically react with the first monolayer to grow a compound. In an ideal ALD system, thickness is controlled simply by counting reactant pulses. As previously mentioned, atomic layer deposition consists of a series of self-limiting reactions. For instance, to build a compound AB using precursors A and precursor B, you would basically need to use a self-limiting reaction of reactant A, where you introduce reactant A to the reactor. It coats the surface completely, with any excess reagent being vacuumed away. You would then introduce precursor B into the reactor. This would form a monolayer on top of the A surface, with any excess being vacuumed away. The basic mechanism of atomic layer deposition is that it always forms a monolayer if sufficient precursor is present and it is in an ALD temperature window. What is an ALD temperature window? The ALD temperature window is a temperature where it is sufficiently high to prevent condensation to form multi-layers. It is sufficiently high to allow surface reactions to go to completion, but it is not too high to cause desorption from the surface. Atomic layer deposition is useful for highly conformal growth, low temperature growth, and atomic scale thickness tuning. It also produces very low particle counts. The disadvantages of ALD are actually quite similar to the advantages of ALD. Highly conformal growth grows everywhere, and you may not require this in your application. Phase selection may be difficult in low temperature growth. Additionally, atomic scale thickness tuning may make thicker films not viable by this process. Additionally, precursors are not available for all materials you may want to grow. The Tyndall ALD facilities include a 300mm applied materials reactor system, 3 200mm research tools, including a Picasun R200 with in-situ monitoring capability, a Cambridge Nanotech VCO Fiji machine, a dual-chamber Cambridge Nanotech VCO machine, which is situated in the silicon fabrication facilities. In addition, we also have some smaller 25mm systems for custom experiments. With the exception of the home-built test system, all reactors are capable of plasma-enhanced ALD in addition to thermal ALD.